My name is Moo-Ryong from USC, as I introduced. So today I'm going to talk about P3, so novel way to preserve our privacy when sharing photos. So cloud-based photo sharing services, henceforth I term PSPs, are becoming very popular nowadays. So people take photos using various smart devices and share them using wireless network using PSPs such as Facebook, Flickr, Instagram, etc. However, there are serious privacy concerns. So here's an example. So suppose that Alice has a secret picture of a nice guy and want to share it using PSPs. So in this particular scenario, so the first possible privacy concern is the unexpected exposure of Alice's photos. So this could happen either by accidents or careless system design by PSP. The second problem might be that we cannot prevent the PSP's data abuse. So in this example, the PSPs may use their best possible inference algorithm on Alice's photo and may draw conclusions like this. So the Alice might be interested in this guy. So, however, currently there is no way to prevent this scenario. We need to completely trust PSPs to share our photos with our friends. So I was not making up artificial threats, but they are real ones. Here are 4 recent news headlines. The photo bucket system unexpectedly exposed users' photos because of their, I would say, naive system design. The problem was their photo URL was too easy to guess, so what the attacker needs to know was just a user ID. Besides, Facebook had a face recognition API in their web-based data API specification, but because of privacy concerns, partially described in this slide, they eventually shut down the API. And not a long time ago, the Instagram tried to change their terms of service, saying that they can sell users' photos without having data owner's permission. But it generated huge concerns, and company reverted back to the original term. So as we observed, these privacy concerns are real to many users. So on the other hand, PSPs provide useful processing for mobile devices. So let me give an example again. The Alice has a brand new smart camera and want to share a high-resolution photo taken by the camera. It uploads to a PSP system. So her friends may have a mobile device with different screen sizes. Then, in order to provide desirable user experience, the PSP scale the image appropriately and send them to different mobile devices. So these types of processing, so-called image scalability service, enables users to significantly reduce network latency and bandwidth usage. Also, it is possible that the PSPs can perform other types of processing, the filtering operation to enhance image quality, etc. So cloud is already doing processing for mobile devices, and they are often very useful. So the main challenge in this work is we want to have both privacy protection and cloud-side processing. So solving this problem, especially under practical constraints, is quite tricky. Then how do we solve this problem? So if we're talking about our approach as the potential alternative, one may immediately think that why not just encrypt everything? However, the photo is fully encrypted on the cloud. The PSPs cannot perform any useful processing on users' photos. As a result, for example, the mobile devices should download full resolution image, regardless of their screen size and storage size limitation, so which is unacceptable in our setting. So if a photo is fully encrypted on the cloud, we will lose the image scalability support and other useful processing benefits. So before discussing our approach, here is the goal, threat model, and assumptions that we made. Again, our goal is to protect our privacy while maintaining cloud-side processing service. The attack model covers 2 categories of threats. First, the unauthorized access, and second, the application of automatic recognition technology on users' photos. So our trust boundary is in between mobile devices and the cloud, so meaning that we completely trust mobile devices, hardware and software. So those include sensors on the smartphones and operating system code, apps, etc. And we don't trust others, including eavesdroppers on the network and PSPs themselves. For PSPs, we assume that they are honest but curious. So which means, again, they will not change what they are doing for users' photos no matter what. But they will try to infer users' personal information using their best possible method. So now we are ready to describe our approach in high level. Suppose again the Alice want to share a photo with Bob. From the photo, we first extract some data which has very small size but has most visual information, which we call a secret part in this talk. So you can think it as most significant bits of entire image binary data. So after removing a secret part, what remains as a large volume but has little visual information, which we call a public part in this talk. And public part is a standard JPEG image, so PSPs can accept it without changing their system. So one can think it as least significant bits of entire image binary data. So when sharing, the secret part will be cryptographically encrypted and ideally embedded inside the public part. Then the image is uploaded to a PSP system. This way, PSPs can perform useful processing on the public part, which is a standard JPEG image. So in this particular example, they scale down the image for mobile devices. So when Bob wants to see the photo, he will download both public and secret part and combine those two to reconstruct the photo. To enable this capability, we have several important requirements. First, our algorithm has to ensure privacy on the public part exposed to a PSP system. Overall storage overhead should be minimized. MP3 encryption and decryption process should be lightweight. And our public part should maintain a standard compliancy, in our case, JPEG image. Cloud providers should be able to perform processing on the public part. And our resulting system should transparently work with existing PSP systems. So overall, our algorithm and system, called P3, achieves these goals and requirements. So in the next couple of slides, I will describe how and why our algorithm and system works. So before describing P3 encryption and decryption algorithm, so I want to share the intuition behind the P3 algorithm. So how do we extract small but important information from the given image? So in this work, we focused on widely used image format, a JPEG image compression standard. When compressing the image in JPEG, an image is divided into many small patches, like this. The size of one patch is 8 by 8. On these patches, JPEG performs DCT, the discrete cosine transform. So then, each location on the left grid corresponds to different frequency values. If we draw histograms using all coefficients from the all patches in the image, they will look like this. The center position of each histograms have 0 values, denoted as blue lines in the slide. So from this, the first fact that we can exploit is that the DCT coefficients of natural images are sparse. So in general, the more energy is concentrated on the top left corner, so which has low frequencies. And especially zero frequency coefficients are called DC components and has significant visual information. This is a well-known fact in image processing community. Second, we see that the signs of coefficients are evenly distributed since histograms are mostly symmetric. So if we take out those values, it will be very hard for attackers to correctly recover the values. Third, the magnitude of coefficients certainly have some information. So to exploit these facts, the P3 take all 3 components out to degrade the public part as much as possible. So now we are ready to describe P3 encryption process. From the original image, we get the quantized DCT coefficients. First, we take out the DC components, which has significant visual information. For remaining AC coefficients, we cut their magnitude using a fixed threshold T. Then each cropped regions are treated separately. So inner part of the coefficients will form a public part, so which becomes another JPEG file, and that can be stored and processed by a PSP system. And outer part of the coefficients will be combined with the DC components and form a secret part. So which has, again, significant visual information, and it will be cryptographically encrypted when it goes out of the mobile device. So note that we successfully eliminate 3 important components that I discussed in the previous slide: DC, and magnitude by thresholding, and signs taken for a secret part. Now we have a P3 encryption algorithm the next obvious question might be how well this algorithm works in practice. So I implemented the proposed encryption algorithm. The first result to show is the threshold versus storage trade-off. So we applied our algorithm on INLIA dataset, which has 1,491 different unique images. The x-axis in this graph is P3 threshold used, and y-axis is the normalized average file size compared to original image. So naturally, all original file sizes are all 1 in blue color here. And secret part is in red, and public part is in green, and some of the public and secret part are in black. The result looks very encouraging. So even if we consider the worst case, the total file size increases only by 20%. So for individual file size, so sizes of public and secret parts are almost even as threshold 1. And after that, the volumes are moving toward the public part as we increase the threshold. So based on this size trade-off and the privacy evaluation on the public part exposed to the PSP system, we set the PS3's operating range as 1 to 20. Then the next maybe obvious question is, what information will be exposed in our operating range? So I used one example image in USCCP dataset that contains canonical images. So when you set the threshold as 20, I hope this is visible, but some structure is exposed, but depending on your background, one may have a hard time to figure out what is in the image. So if I decrease the threshold, the public part becomes more secure, the less structure. So this is 15, and 10, 5, and 1. So for threshold 1, visually it is almost impossible to recognize anything. So for your reference, this is original image, and I'm going to show the secret part with their threshold. This is secret part with threshold 1, 5, 10, 15, and 20. So naturally, as we increase the threshold, less information will remain in the secret part, and more data will go to the public part. So we have seen how P3 encrypts the image and its basic trade-off. Then how about the decryption? So it turns out that in our setting, we are facing one very interesting challenge when decrypting the image. This is caused by the cloud-side processing. So again, as an example, the analyst want to share a photo with Bob. Since the public part is saved and processed by a PSP, the Bob will receive the unprocessed secret part with a processed public part. Then the challenge here is that given these information on the receiver, can you reconstruct a processed version of original image on the receiver side? So if the original image can be written as a linear combination of secret and public part, this problem becomes more straightforward. But it is not the case in our setting because P3 encryption process hides the sign information on the public part. Then how do we solve this problem? So as I said, the original image is not just a combination of secret and public part, the linear combination of secret and public part. So it turns out that the original correct equation for the original image must include a compensation term C. So in the paper, we show that this compensation term C can be derived from the secret part S, which we already have on the receiver side. Therefore, P3 can handle any linear processing. For photos, this linear processing term can handle many useful functions, from scaling, cropping, to sharpening, blending, smoothing, etc. So based on this P3 encryption and decryption, so we design a P3 system that can transparently work with existing PSP system. P3 takes an interposition architecture, so it requires trusted man-in-the-middle proxy on the device, as well as the cloud-side storage space that stores encrypted secret part. It would be ideal if we can store an encrypted secret part inside the public part and use the PSP system as a storage. However, in reality, most PSPs will eliminate embedded binary inside the JPEG image when they receive the photo from the users. So we take this alternative approach based on the external storage space. So in our system, on-device proxy will perform P3 encryption and decryption when it upload and download photos. And cloud-side storage space will store the encrypted secret part. And public part will be stored and processed by a PSP system. So P3 architecture is fairly easy to be implemented with existing PSP system, such as Facebook and Flickr, etc. And we don't require to change their infrastructure. So we actually implemented all necessary components, algorithm on the device and the cloud-side components on Dropbox. Here is the screenshot and delays on the P3 encryption and decryption on the device. So as you can see, the receiver without relevant password or key will basically see gray-like image instead of the original image on the left side. And also, delay numbers are moderate on the phone. So P3 is practical and can be implemented with a real system, such as Facebook. Also, we extensively evaluate privacy aspect of P3 using PSNR and a representative set of computer vision-based recognition algorithms. Those include safety feature extraction, edge detection, and face detection and recognition. So essentially, all results are saying that the PSNR is so low in public part, and all these recognition algorithms becomes useless with a public part. So P3 preserves privacy. So in this talk, I'm going to show the one result on face recognition. All detailed other results are in the paper. So if you are interested in, please refer the paper. So here is the setting for the face recognition evaluation. So we use eigenface algorithm with a Calafell face database designed by the NIST. We also use Colorado State University's face recognition evaluation system. Essentially, this evaluation system gives us a ranked list of faces in a decreasing order of similarity as an answer. We examine the recognition performance under various settings. So combinations of different testing sets, different distance metric, different P3 thresholds, and additionally using public part of a training set as a new training set to mimic the advanced attacker. And here is the result on the worst case. The x-axis is a recognition rate, and the y-axis is a cumulative recognition rate. X-axis is a recognition rank. So the top line in the graph is a recognition result based on normal training and proving sets. And the two lines below, green and red line, are the recognition rates based on public part as a training and proving sets. And each line uses a different threshold. The green line uses 20, and red line uses 1 as a threshold. So let's consider this point first, which has the best recognition rate from the perspective of an attacker. So it has a rank 50 and the rate about 40%. So intuitively, what it means is that for an unknown face, there exists the right answer among top 51 candidate faces with 40% probability. So to make it a little easier, here is the recognition rate about the best candidate. So we only care about the best recognition result. Then the green line has 15% recognition rate, and the red line has only 2% recognition rate. But even if the attacker gets 15% recognition rate, as in the green line, she only has a public part, so it will be very hard to verify whether the result is right or not. So the face recognition becomes useless. Additionally, the all other results using a different threshold and using a normal training set shows the worse recognition rate than the green line presented here. So overall, P3 breaks the face recognition. So summarizing P3, so our algorithm and system, collectively called P3, provides privacy-preserving photo sharing while maintaining a cloud-side processing. We proposed a novel image encryption and decryption algorithm, and also presented a complete system design that can transparently work with existing PSP system. And we built a complete prototype and also performed extensive evaluation on the privacy aspect using a computer vision-based recognition algorithms. And thank you, and I'd be happy to take any questions.
Nikita Borisov, University of Illinois. Very interesting work. Just one clarification and one question. The clarification is when you say, when you show pictures of the secret part, this is all the information you can recover from just the secret part without knowing the public part. Is that correct?
Secret part is a part of information from the original image. So,
right. So from the secret part, you can, in theory, recover the image even without the public part, correct?
no, you need a public part to correctly recover the original image.
Okay. And the other question is, you mentioned that you worked in an honest but curious model for the PSP. So what would be, are there any privacy challenges that exist with your system if the PSP is fully malicious? I mean, I don't see, it doesn't, it's not immediately obvious to me, so.
Yeah, if the PSP is malicious, our system will break. So.
How so?
Sorry?
If PSP is completely malicious, then you say your system would break?
Yeah.
How so?
PSPs can identify the systems because we crop the coefficients using a fixed threshold T, etc. So maybe they just eliminate our apps, etc.
So that wouldn't be a privacy problem, though, right? That would be just a functionality problem. Are there privacy challenges? I guess that's what I'm asking.
Privacy challenges, I don't think privacy aspect will be preserved. So
okay.
Yeah, they cannot do anything. Yes.
Thank you.
You're welcome.
I have a question. So following up Nikita's question about if the... Can you hear me? Okay. So if you cannot identify the faces from the secret part either, then why is it necessary to keep it secret?
You can identify faces in the secret part if you can access to the secret part.
Oh, okay. So in the secret part, there is enough information to retrieve all the features even without the public part.
In terms of recognition technology, maybe yes.
Okay. Can I ask a very high-level question? This is in large part, this is because of my ignorance with the image processing literature. At a very high level, one of the most counterintuitive things about this work is that most of the visual information is in the small part of the picture or can be pulled out into an image that actually takes very little space. Whereas there is a big part of the image or the part that takes more space that has very little information. Is there a way you can, do you see the counterintuitive aspect of it? And is there a high-level intuition for why that is the case?
So I think that is related to, why JPEG works. So so we transfer the pixel domain information to the coefficient domain the information. Then the low frequency, the components has most structure. So we in our scheme, we take out the coefficient domains, the most significant bits, essentially. This way, we preserve most structure on the secret part, and the remaining public part has most this enhancement layer, or details of edges and dots, etc. So, yeah. That's your question.
Yeah, Lakshmi from NYU. Can you comment on this privacy guarantees of the whole P3 scheme? So because I'm a little bit worried about that in the sense that JPEG is a continuous space, and even if you hide information in the high dimensional coefficients, you can substitute random values and check out different points in the space. And you might be able to define certain smoothness functions of what you expect in normal images and try to figure out how to attack P3. And I'm not sure whether P3 is completely defensible against certain types of attacks. And
right, yeah. This is a very good question. So short answer is we don't have a mathematical guarantee of our scheme yet. But as far as we know, we are not aware of any signal processing or image processing based technique that can break our scheme. So we tried the representative set of the computer vision based techniques, which has all essential building blocks in signal and image processing communities are using. So that's our current state. We are actually trying to prove the guarantees using mathematical tools, etc. right now.
Thank you.
You're welcome.
We'll have to, unfortunately, because of lack of time,